Today we're going to figure out how to go from Cartesian to polar. I actually have the Cartesian axis. We have our y-axis. I'll label it. And over here we have our x-axis. If I go like this amount in x, and I go this amount in y, right here, called x, y. Now, how do I translate that to polar? Polar means instead of x, y, we're going to have something called r and phi, distance away from the origin, that we'll call r, and we have some angle away from x that we'll go ahead and call phi. So, how do we translate between these two? Project this down onto the x-axis and project this onto the y-axis in order to find out what the components of this are. So, in order to do that, let's go ahead and project. So we have this piece, and we have this piece. We'll go ahead and move this piece over here. So, from this diagram, we can say x equals and y equals. So let's look at x. X has some length, and it's also projected down here by this angle. So what we're going to say is it's the length r, which the original green line was, and we want to scale it down by cosine of phi based on the angular relationship between this and this. Also, conceptually, what this means is we're scaling r down. So cosine can only be 1 at a maximum and at the other angles, except for where we start to repeat in periodicity, we're going to have lesser values than 1. Depending on what this r is and what this theta is, what this phi is, we're going to have a smaller or up to r size x component, and it's given by this expression. Similarly, when we examine y, it's the opposite angle, so we say r sine of phi. So now that we have x and y in terms of r and phi, the red, which we started with and we wanted to translate to green, we're going to have to find the rate of change of this with respect to this, and the rate of change of this with respect to this, and then come back to x and take the derivative with respect to phi, and then come back to y and take the derivative also with respect to phi. So we'll go ahead and do those. dx by dr, we can see this is going to become a 1 because it's being acted on by this operator, ddr. And x lets us know we're doing it to this function up here. So we're just going to get cosine of phi. Then we'll go ahead and do the dx d phi. I'll do it up here. And this is going to be equal to the constant times the derivative of cosine of phi, which is minus sine of phi. Then, if we go ahead and do dy by dr, That's just going to be sine of phi for the same reason as before. And dy by d phi is going to give us r, which is the constant, times the derivative, which is cosine of phi. Okay, so what we're actually going to do is find the determinant of this. So I'm going to use my diagonal downs minus my diagonal ups method. So this guy minus this guy. So the diagonal down is going to be r cosine squared phi, this one times this one, minus this one times this one, r minus sine squared phi. Okay, bring this guy out. We'll turn this into a plus. Becomes a plus as well. Recall that there's a trigonometric identity. This one and this one becomes 1. So let's go ahead and factor out an r times this plus this, which is 1. So all we're left with is r. So that lets us know that when we transform from this coordinate system, x and y, to this coordinate system, we need to apply an extra r. This is known as a Jacobian factor, and typically we're going to need to represent it as r d phi dr when both phi and r are changing. When r is constant, then we just have r d phi, and when phi is constant, we just have dr as the Jacobian factor, which we usually use as like an integrating factor for different situations, depending on if we're going to be doing areas or single dimensions, because this is a two-dimensional operation that we performed from the 2D xy to the 2D r phi in order to achieve the polar coordinate transform. Alright, thank you.